Hello. Fluid mechanics. Why is it stuck here? Oh. Hello everyone. So welcome. I afraid I cannot show my face. There. Ni. Internal flow. What happened here? Okay, so kau ada pintu tak? Okay. Hai Dijol. Boleh dengar? Kalau boleh dengar, cakap boleh dengar. Okay. Hello everyone. Okay, terbaik. Okay. Okay, sekejap kita share link kat semua orang. Hello Mubashir. Beres-beres. Okay. So tahu lah, aku nak tunjuk muka aku sebenarnya. Okay, sementara tunggu tu. Okay. Hello everyone. Boleh nampak tak? Selawat lah. Sekejap, mana? Okay, so malam ni kita nak buat fluid mechanics. It's an exam. So, okay, kita start Okay, so kita akan go through the first chapter, dimensional analysis. Lepas tu internal flow, external flow dengan pump characteristics. Sebab turbo machinery punya chapter tu korang tengok buku teks je, tak payah ada banyak sangat background yang korang kena tahu awal-awal lah. Okay, wait, let me video. Okay. Hai, thank you Acap. Okay, so kita pergi dimensional analysis dulu. Okay, so dimensional analysis. So what do we have here? Kita ada dimensions and units. We have dimensional homogeneity. Okay, so dimensional homogeneity is making every other equation have the same units. That is what they call homogeneous. They are dimensionally homogeneous. For example, which the total change of energy. Another example is the Bernoulli's equation. So dimensionally homogeneous for total energy is the units here, which is ml squared over t squared. For Bernoulli's equation, it is m over t squared l. So maybe in the exam they can ask generate a equation that has homogeneous dimension, or an equation that is dimensionally homogeneous. Okay, so this is our three main primary dimensions: mass, length, and time. So the most important units that we need to have is we need to know is the force. Force is mass times length over time squared, ml over t squared. Okay, so this is a very important unit because most of the equations that we use in physics usually involve force. Okay, so we have non-dimensionalization of equation. What is a non-dimensionalization? Non-dimensional equation is when you divide each term in the equation and the product has the same dimensions, but the dimensions is zero, which is like meter over meter, something like that. It cancels off by itself, so it's just 1, so it has no units. Okay, so we have here normalized equation, non-dimensional parameters, which will be further discussed. We have parameters, which is dimensional variables such as length and time, which is the primary dimensions. Non-dimensional variables, angle of rotation, theta. So theta is a non-dimensional variable, which also means that radian per second is theta per second. So it's actually the unit is minus s. Okay, so for now that is the unit for, if you guys have been wondering lah, because one of my friend asked me about the units here. So radian per second, radian is not a unit, radian is theta. Theta does not has any dimension. It is just indication of the circle unit. Okay, and then we have dimensional constant, which is g. Okay, so they will ask you what is the advantages of non-dimensionalization. The number of parameters in a non-dimensionalized equation is less than the number of parameters. The relationship between key parameters in the problem are identified because there are so many parameters and you need to find each relationship within the parameters. Okay, so so we move on to dimensional similarity. We need to in order a model or a prototype to be similar, we need to have dimensional similarity, which is the first one is the geometric, dynamic, and kinetic. Okay, so this one boleh je baca sendiri. Okay, so sometimes the question will ask you about experimental testing. Experimental testing includes like submarines. Okay, maybe they will ask you about submarine. We learn in external flow about aerofoil. We also learn about maybe they will talk about like columns, long cylinder. So maybe they will ask about the testing experimentally between the model and the prototype. Okay, so sometimes it is not always possible to match the parameter of the prototype and the parameter of the model, which is called incomplete similarity. Okay, so I have simplified here. It says that the Reynolds number for the prototype does not always equals to the Reynolds number for the model, because usually the model is much smaller than the prototype. Okay, so this is one of 4 ways to encounter this problem. We usually use the 4th one. Okay, so now we're moving on to the method of repeating variable. Okay, so this is actually just a recap. So this actually a question in 2020 past year final. Okay, so it gives us a condition, and then it gives us the parameters. Okay, let's padam. Okay, this was the last time we did this together. Okay, so we have force, lift force 1, we have angle of attack 2, characteristic length 3, velocity 4, this is 5, this is 6, this is 7. Okay, so from here you can identify which one is a independent and a dependent parameter. Okay, there are 7 parameters. Okay, so what is a independent and dependent parameter? So okay, the first step is to list the parameters in the problem. So we already know the number of parameters. Now we need to determine which one is the independent and dependent parameter. So the dependent parameter is usually the parameter we want to find. The independent parameter is usually the parameter we can control. Usually the parameter that we want to find is for lift, drag, elevation of ball after it bounces, shear stress of the skin friction at the surface. Okay, that is the dependent parameter. What we can control is the density, viscosity, mass velocity, length and constants. So you can you can already like see which one above here is the dependent variable, which is the force. Okay, other else is all dependent. Velocity dependent. We can control the length, we can control the angle of attack, the density, the viscosity, and also the Mach number is also controlled. So moving on to the second step is list the primary dimensions of all the parameters, MLT. Okay, so angle of attack here is theta, so it is already a non-dimension parameter already, so it has no units. Okay, so this is we move on to step 3, which is the Buckingham-Pi theorem. Okay, so we have now list down all the primary dimensions. Now we need to calculate K, the expected number of non-dimensional parameters or pi's. How many pi's do we need? How many pi's does it needs for the condition? Okay, this condition here, berapa banyak pi kena ada? Okay, your pi dimensionless. Situ. Okay, so K equals to n minus j. N is the number of parameters, j is the reduction number. So if MLT exists, j equals to 3. If only 2 of those exist, j equals to 2. Okay, so that is quite easy. So now we can see that n is equal to 7 and j is equals to 3. So K equals to 7 minus 3 is 4. So we're supposed to have 4 pi. 1, 2, 3 and 4. Okay, for this situation. Okay, where is it? Okay, So we need to choose J repeating parameters. So J is the number of reduction. So we also have to decide on how much parameters do we need to keep constant. Okay, so there are 3 total parameters that we need to keep constant. And then this is how to choose the repeating parameters. Repeating parameters cannot be the dependent parameter. So it cannot be force, leaf force. Okay. Also make sure all of the repeating parameters include MLT. Repeating parameter cannot be complicated. Okay. Why is it cannot be complicated? Because it will make it harder for the non-repeating parameters to be cancelled out. Okay. So what does that mean? It means that usually the repeating variable don't have all MLT. It sometimes only have MLL or T. Okay. I hope you understand that. Okay, so basically for the repeating parameters, we can always also refer to the list of non-dimensional parameters that we already learned. So this is the list of non-dimensional parameters. The other parameters you don't need to worry about. So since tomorrow is like open book test. Okay. So wait. Okay, so you guys can open your books. Like, where is it? Chapter apa? Aku pun tak ingat. Okay. Sini ke? Okay. So you guys must remember now that tomorrow, that when you open your book during the final, so the page of the non-dimension is 315. Okay. Tak nampak kan? Tak apa. Tapi sebab buka buku nanti, korang tengok je buku. Just ingat nombor page je. Tanda siap-siap 316 dengan 319. Okay. Okay, so now we could move on to constructing the non-dimensional parameters. Okay, so usually the non-dimensional parameters which we have concluded here to be 3, there are going to be three repeating parameters, which is the velocity, the characteristic length, and also the density. So only the repeating parameters have the power of A, B, C, and the non-repeating only have the power of 1. Okay, so as you can see here, the force only power of 1. So the other repeating parameters is A, B, C. And also note that A, B, C can also equals to 0. Why does it can also equals to 0? Because let's say we have the angle of attack. Angle of attack, there is no dimension at all, kan? Macam theta. So you don't need any dimension. You don't need other units to cancel out the dimensions, because there's no other units in the theta. So A can equal to 0, B equal to 0, C equal to 0. So that's why we say that angle of attack is already a dimensionless parameter by itself. Okay, like that. So let's say we have the Mach number, and then A, B, C. So sometimes B equals to 0, C equals to 0, but A equals to 1 or negative 1 in this case, because the Mach number is L over T. The velocity is also L over T. So we can cancel out this, which is the B and C the power will be equal to 0. Okay, so pi 3 will be Mach number. Okay, so let's write here. Pi 1 will be force diff. Pi 2 will be Reynolds number. Why? Because we use the viscosity as the non-repeating parameter. Pi 3 will be the Mach number, and pi 4 will be the, what was it? The angle of attack. So there you go. So this is how you answer this sort of problem. Okay, so let's move on to internal flow. Okay, so far so good kan? Okay, is everyone okay? Now we move on to internal flow. So in your textbooks, internal flow is on page. Internal flow actually has a lot of important pages that you guys need to tanda lah. Nanti kita bagi tahu. Okay, so right now, wait. Okay, so internal flow, we have turbulent and laminar flow. Laminar is a smooth, streamlined, highly ordered motion. Turbulence is velocity fluctuation in highly disordered motion. Transitional flow is the flow that fluctuates between laminar and turbulent. Okay, so internal flow is actually very important because it will be used in turbo machinery also. Okay, let me just put that. Used in turbo machinery. Oh my god. Okay, tak apalah. Okay, abaikan. Okay, so let's see. First of all, we should go see the Reynolds number. So the Reynolds number is the ratio of initial forces over viscous forces. If the Reynolds number is large, it means that it has a very big relative, and the initial forces is too large relative to the viscous forces. If it's small, the viscous forces are large enough to suppress the fluctuations and clip the fluid lamina. Okay, so the lower the Reynolds number, the more lamina. The higher the Reynolds number, turbulent. So what is this fine line between lamina and turbulent? We call this fine line as the critical Reynolds number. So actually, the critical Reynolds number differs from different fluids, differs from different conditions. Usually, if it's not this one here, it will be stated by the book, which is usually for some aerodynamics condition, the RECR is equals to 1 times 4 for aerodynamic. Macam tu lah. But for now, we stick for circular pipe. Reynolds number is less than 2300. Turbulent will be more than 4000. Okay, so from there we can see this is the hydraulic diameter. Hydraulic diameter, you can see this formula in your textbook. So this is the entrance region. Not much lah really. You just need to understand that usually we assume the flow to be fully developed. This is how the velocity profile develops. Okay, so they can ask you, how does a turbulent let's try here. Fully developed turbulent flow versus fully developed laminar flow. The laminar flow looks like this, but the turbulent flow looks like that. So if they ask you to sketch or graph, you already know lah how to graph it. Okay, so this is both different. Although both of them are fully developed, the velocity profile will be different. Okay, that's all. So that's the entrance region. You can see the simplification of how do you want to find the length of entrance, entry length. Okay, so this is the laminar flow in pipes. So okay, this is quite a lot, so let's go sikit-sikit. Okay, so the velocity profile of a laminar flow is given as this. This is what masuk midterm test hari tu. Quite upset lah. So I don't expect it to masuk final lah. Okay, so the assumption is consider steady laminar incompressible in fully developed region. Okay, so now we masuk laminar flow in pipes. So there will be laminar and turbulent. There will be pressure drop. Why are there pressure drop? There a pressure drop due to friction. So there are a lot of ways for you to find the friction factor. For this, there are a lot of ways to find friction factor and also a lot of parameters if you don't have. So this one, they give you the skin friction and also the viscosity and the velocity, but usually they don't give the skin friction. Ni nama dia skin. The shear friction. If it's given, then you're lucky, but so far I haven't come to that. This is the friction factor for laminar. As you can see, it is quite linear. So from here, from this equation, we can we have a derivation came up by Poussier's law. Okay, so this is the pressure drop and this is the equation. Okay, so from there we can conclude that the pressure drop is what is this berkadar terus, directly proportional to the length of the pipe. The diameter is inversely proportional macam tu lah. Okay, so effect of gravity semua tu, I don't think this lah masuk lah, tapi just recap lah kalau masuk. Quite important is the ni this is the turbulent shear stress. Okay, let's just singgah apa yang patut lah. So this is the turbulent velocity profile. We will also touch this in the external flow. External flow pun ada benda ni, sama je. Dia ada juga yang layer ni. We will find out later. So this is all the names that they come up with. I don't know why there are so many. Okay, anyway, so kan cakap tadi ada banyak cara untuk dapat friction factor tu. So this is the first equation. The first equation here, if you notice, there are two, F on one side and F on one side. So we also can approximate it and become F on only one side. So this is what we call the Haaland equation. Okay, that's the difference between the Haaland equation and the Colebrook equation. The Haaland equation does not have F on one side. Does not have F on both sides. It only has F on one side. So the Haaland equation is used for smooth and rough pipes. What happens if you have only smooth pipes? The roughness will be equals to 0. So there will become a new equation which is called the Prandtl equation. Okay. So this is important actually. Page 371. You guys can open your books to page 371. You can see all the roughness here. So I just answered the past here. It asks us which material do you guys want to use. So if you want to use cast iron, this is the roughness. If you want to use glass or plastic, this is the roughness. So okay, quite important there. So minor losses. Minor losses also plays an important role in the pipe networking and turbo machinery, because it requires you to calculate the head loss in components. Okay, we will talk about that. Okay, so for minor losses, so the minor losses is here. Wait. Okay, here. So this is all the components that can contribute into the minor losses: fittings, valves, bends, elbows, traces, inlet, exit, enlargement, contractions. It will all interrupt the smooth flow. Why does it interrupt the flow? Because it introduces flow separation, irreversible deceleration, and also mixing. Flow separation is also in external flow topic, so you guys need to pay attention in the flow separation. Okay, so wait. Okay, so where is it? Page 383. So you guys can open to page 383. Okay, so at page 383, this is the whole page for the minor losses. So you guys boleh tanda lah, siap-siap. Nanti esok you guys buka je. So dia ada banyak lah cerita pasal types of bands, types of components. Okay, so just take note. Okay, resuming. USB video. Okay, page 383. Okay, so minor losses. Okay, so KL is what we call as the loss of coefficients. 378 ni apa? Tak apalah, nantilah. Ni lain kot. Okay, so this is the equation. HL is KL equals to HL over V2 squared over 2G. But we don't use this because usually we want to find the head loss. We're not finding the loss of the coefficient here. So we turn here. So this is the total head loss. Total head loss is the major head loss plus the minor head loss. So if the system changes the diameter of the pipes, you guys need to separate the major loss and the minor loss. And also if it's okay, wait, let me see. Usually for a system, there's like the suction and the, what do you call this, apa yang lagi satu tu tak ingat suction dengan apa start dengan D. Sekejap, wait, external flow, never mind lah. Sekejap, apa yang nama dia? Discharge. Okay, so this is like just quick sneak peek. Okay, so if your system, okay, let's say this is your system and this is your pump. If your area here is same, area 1, area 2, if area 1 equals to area 2 same, then you can use the minor loss plus head loss. HL plus HL equals to H major plus H minor. But if the area is not same, then the velocity will also not be equal. So this might be slower and this might be faster, something like that lah, because it changed. So you need to consider the major loss, major plus H minor over here, and also H major plus H minor separately, and then baru you tambah, sebab they will have two different velocities. Okay, so over here we assume that the change of velocity equals to 0. Change of velocity equals to 0 because the flow rate and the cross-section area is constant. Okay, so that is serba sedikit lah pasal ni, inlet and outlet. Okay, so this is inlet and outlet. If the inlet equals to the outlet, if there is no change in diameter, then you guys can use this equation, which is quite simple. HL equals to FL over D plus total of coefficients darabkan dengan V2 over 2G. Okay, so that is the minor loss. So piping networks, piping networks, H pump, horsepower of pump equals to elevation difference and plus H loss. Dr. Chu always talk about the efficiency, desired output over required input. This is important for the pump, because usually they ask you what is the efficiency of the pump, what is the power of the motor and power of the shaft. Okay, so principal analysis, nothing there. Okay, so that is minor loss. Rate velocity, not so important, I don't know. It's important, I don't know. Discharge coefficient, tak ada kot, tak ada sangat kot. All of this is quite already in your textbooks, so don't need to worry. This is the flow meters. I have simplified the flow meters here. This is liquid fluids and gas fluids. Maybe they ask you if there is a liquid system, which flow meters do you guys need to choose? If it's a gas fluid system, which one you need to choose? Like that lah. Okay, so that is internal flow. Now we masuk external flow. External flow is a flow over bodies or rigid bodies. Okay, so we come here first. Free stream velocity. Free stream velocity is the velocity of the fluid, assumed to be uniform and steady. So there are two type of flow, not two lah. There are two ways to analyze the flow, 2-dimensionally and 3-dimensionally. So we usually assume the analysis to be 2-dimensional because we usually assume that the body is very long, it has a constant cross section, the flow is normal to the body, axial velocity equal to 0, which means that there is no velocity along the wait. Hold up. Okay, I have kan cantik ni. Tengok aku lukis cantik. Okay. So assume that this is the cross section of the body is just constant, like this aerofoil, and there is no velocity in the side force direction. There's only velocity in the flow direction. Okay. So we can also assume the flow to be axis symmetric if the rotational symmetry is about an axis, like a bullet. Okay, put here. Bullet. Bullet. Okay. Okay. What about three-dimensional flow? Three-dimensional flow is the flow parameters that vary in three coordinate direction: Vx, Vy, and Vz. It has multiple flow direction. Over here, you assume it to be normal to the body, but for three-dimensional flow, it has multiple direction, and it also have n effects, induced drag. Over here, we assume the body to be very long, so the n effects to be negligible. Okay. So external flow, there are two types of forces that induce from external flow, which is lift and drag. So lift is the sum of pressure and wall shear forces in the direction normal to the flow. Okay, so what is important between lift and drag is the direction. So drag is the force of flowing fluid exerts on a body in the flow of flow direction. So this one is normal, this one is in the flow direction. Okay. So the coefficients are basically the same. The difference is just the forces on top here. Okay. So this is the resulting force. Okay, so usually if you are given a free body diagram, this is how it would look like: the lift generated by the body and also the drag generated by the body. Okay, so how is lift and drag generated? So from here, we assume that pressure or static pressure exerts on every surface, on every direction of the surface, but when the velocity of the fluid is faster, the pressure decreases. Okay, let me write here. When velocity is faster, the pressure decreases. So over here you can see that the pressure is small. Why is it small? Because it is, the V is higher. Okay, why don't you compare it over here? The P is bigger. Why is it bigger? Because the V is lower. So the difference in pressure, okay, so this is small, this is big. So this is small, P big minus P small, you will get something like this magnitude. This magnitude is what we call lift. Yeah. So lift is the, okay, wait. The sum of pressure and wall shear. Okay, so this is important. Okay, the sum of pressure, because the pressure over here is smaller and pressure over here is bigger. So why do we assume this to be? Is from the Bernoulli's equation. Okay, so we all know that. Okay, so that is lift. What about drag? Drag, there is two types of drag. Drag caused by friction and drag caused by pressure. Okay, so I have these figures here. So if the flat plane is like lepe here, the friction will be higher. But if the flat plane is perpendicular to the flow, the pressure will be higher. Okay, why is it like that? Okay, so this is friction drag. Friction drag is due to the wall shear stress, aka skin friction parallel to the flow. And the strong function of viscosity, because the shear stress is viscosity. Shear stress is viscosity. Pressure drag is due to the pressure difference parallel to the flow. Parallel. Okay, max pressure drag when frontal area, max area. Okay, what does it mean to the pressure difference parallel to the flow? Okay, you see here. Okay, guys, take note. Why is my iPad lagging? Okay, pressure difference parallel to the flow. Over here, we got pressure normal to the flow. So that's the difference between lift and drag. This one is the normal to the flow, but this one is parallel to the flow. So you guys cannot be cannot tertukar lah. Yeah. Okay, sorry, iPad lag though. What the fuck? Okay, so friction drag and pressure drag. Friction drag, pressure drag. Okay, let's go here first. So wait. Okay, so what I want to show you before we go through the drag is the difference between blunt bodies and thin bodies. So blunt bodies, the area in the equation here is referred as the frontal area, but for thin bodies, the area is considered to be the planform area. Okay, so take note. Okay, so over here we got flow over flat planes. So this is similar to what we learned in internal flow. We got the turbulent layers and everything, but it all starts as a laminar boundary layer. So this is the irrotational flow region. This is the boundary layer. Okay, so okay. So as you can see here, if the Reynolds number under 5 times 10 power of 5 is considered to be laminar. Okay, so in contrast to internal flow, okay, I said here ni kan, wait, let me correct myself. 5 to the power of 5 for aerodynamic flows. This is for aerodynamic flows. This is for circular pipe. But when we are talking about flat planes, the laminar flow is considered to be under 5 times 10 power of 5. Turbulent to be in between these numbers. Okay, you might ask what happens above this number. It is actually data like approaching Mach number above supersonic. Supersonic effects has different, is a whole different study lah. So actually the turbulent flow is just from this range. Macam tu lah. So this is the flow over flat planes. If they ask you what is the, this is the thickness of the layer. Thickness of the layer, you use this. This is the apa ni? X is the ni X. Okay. So just take note of these two, 1, 2, 3 and 4. Okay. So CF is the what? Coefficient of friction. Coefficient of drag friction. Drag friction average. Okay. So as you can see here, it is Reynolds number dependent. But if you exceed the turbulent flow, it is no longer dependent on Reynolds number. It is only dependent on the roughness. Okay, so that is flow over flat planes. This is the flow over cylinder and spheres. So this is a quite interesting subtopic because usually you would, okay, you can observe here, usually you would assume that if it has a rough surface, it will have a higher coefficient of drag. If it has a smooth surface, it will have a lower coefficient of drag. But for spheres and cylinders, that proves to be not the case. Because sometimes the surface roughness may increase or decrease depending on the Reynolds number. So let's say you are playing golf. So the faster the golf balls go, the lower the drag. Okay. Okay. From here to here, from here to here. Okay, we can conclude that faster golf ball, lower drag. Because we assume the velocity to be directly proportional to the Reynolds number, because that is the incoming air of the the golf ball. Okay, so high velocity, high Reynolds number. Okay, that's what I'm trying to say right now. Okay, so this is just an example of golf ball. You can also see the other examples, but this is actually a very small region, because if you want to observe, okay, wait, let me see, chapter 11, where is it? Sini. Okay, kalau korang perasan, graph tu is only a miniature graph from here. Okay, let me make it bigger. No, make it bigger. Okay, this small section here is represented here. Don't believe me? We tengok Reynolds number dia, 4 times 10 6, 4 over here kan. Okay, what about go over here? So it is just a small representation. So it is actually a very small region. But because of we study this, we need to know why does it actually fluctuates like that. So it's actually over here, located here, if you guys were wondering. So it's actually the faster you go, I don't know. Okay, wait. Smooth. Okay, anyway. Okay, resuming. Tadi mana tadi kita? Okay, kat sini. Okay. So what can we use with this information? We can apply this so that we know that the faster the golf ball, the lower the drag. So if you hit it hard enough, it can actually go much more further, something like that. Okay, so now we talk about flow separation. So flow separation is actually quite interesting. I don't know, I find it really interesting, because flow separation is when a fluid stream detaches itself from the surface of the body. Separation region is usually the low pressure region. It is where it has recirculation and backflow. If the separation region is bigger or larger, it will have a much more larger pressure drag. It will reduce velocity. Okay, as you can see here, it mentions it reduces velocity. What happens when the delta V is negative? It means that there is deceleration. So this deceleration is irreversible. That is where we find the minor losses in pipes. Because, or in the components, my bad. As we have seen in the internal flow. Where is it? Is it? Here. You see here? Dia cakap sini, irreversible deceleration caused by flow separation. Why? Because it reduces the velocity of the flow. That's all. So everything is related. Macam tu lah. So the wake region is the region of the flow trading over here lah. This is the hujung-hujung ni semua wake region. So there are some effects of the separation region. Significant viscous and rotational effects. It will form shedding vortices. It will induce vortex shedding, and then it will cause vibrations, causing body to resonate. Okay, so mana streamlining tadi? Oh, kat sebelah ni streamlining. Okay, we will enter that. Okay, so this one, factors for separation points. Reynolds number, surface roughness, level of fluctuation in stream. So usually this is all in the textbook. I just want to share what I found that's not in the textbook. So streamlining is, how to simplify it, is decreasing the pressure and increasing the friction, which is actually overall decreasing the drag lah. So how do we streamline a body? We increase the surface area, we delay the boundary layer separation, we reduce the pressure difference between the front and the back. So the front and the back is parallel to direction of flow. Okay, so it is considered to be drag because it is parallel. Because sini and sini. So kalau sini lagi besar, sini lagi kecil, ataupun usually sini kecil, sini besar. Macam tu. So dia akan tolak dia balik. Macam tu lah. It's like a reverse lift macam tu lah. Okay. So this is how I simplify things. So how do we increase the surface area? We make the body slimmer. Delaying the boundary layer separation is staying attached to the surface longer. Reducing pressure difference actually reduces the vibration and noise, and also the pressure recovery. Okay. So for example, if you have a streamlined body, you wouldn't have much vibrations. But what if you don't have a streamlined body? For example, you are driving a truck. Oh my god, I am driving a truck. You would hear a lot of noise. So much noise. So much. You know why? Because it is bulky. There are so much of what do you call this? Flow separation. Something like that lah. When you drive the truck very fast, it will produce a lot of noise, and also sometimes it will introduce a lot of vibration because it is not streamlined. But if you drive a car, oh my god, this does not look as appealing as study. Wait, let me draw again. Oh, mana? Okay, jap. If you draw a car, very sexy car. So at high velocities, it will produce much more lower noise. Noise low. No vibration. No vibration. Okay. So that is the difference. So it is better to make a body that usually okay, this is important. You only streamline things when it is moving in a very fast motion, or okay, I put it here. Only at high velocity fluid flow does the streamlining takes effects. At low velocity fluid flow, the streamlining doesn't much effects. Okay, so based on your kegunaan lah, you can streamline, you can choose to streamline or not to streamline. If it's going fast, it's better to streamline, but if you're not going fast, you don't have to streamline. Macam tu lah orang cakap. So this is the blunt bodies and this is the thin bodies. As you can see, the area that it is considered is the BD. BD is the frontal area. Legs, yeah. BD is frontal area. Sini orang guna LD. LD tu LD ni dan ini planform area. Okay, L ni aku tak tahu sebenarnya jadi apa. BD, LD. Pandai lah korang. L ni korang assume length of wing tu lah. Okay, macam tu lah. Okay, aish. Okay. So korang kena ingat juga, do you notice that over here it is L over D, but over here it is D over L. Pelik kan? Sini L over D, sini D over L. Tapi sebenarnya sama je, sebab dia start dengan 0 sampai 6. Sini start with 0 sampai 0.4. So this graph actually is this graph. But they don't, you can, it doesn't, it's not important lah. It's not important. It's just make sure that you guys are aware that this is L over D and this is D over L. Macam tu lah. Okay, nothing much there. Okay, lift here, lift. This is important. Wing loading for an aircraft. Takeoff velocity, max lift. If you want to have maximum lift, you need to have maximum coefficient of lift. Aspect ratio is the span length over chord width. Span length over chord width, BC. Aspect ratio tu lebih kurang macam planform area ni lah. So if you have a high aspect ratio, wait, lag tu. Okay, kita lukis kapal terbang. Okay. Okay, this is what you call high aspect ratio. The wing is long and the chord width is small. Okay, but if you draw something like an aircraft, like a fighter jet, wow, what kind of fighter jet is this? I don't know, bro. Sama. The chord width is, this is what we call low aspect ratio. Okay, this is what we call high aspect ratio and this is low aspect ratio. Okay, this is usually used in fighter jets. This is usually used in gliders. They both have different advantages. If you want to know, the iPad. Okay, if you want to know, this one has higher efficiency. This one has higher maneuverability. Mampus lah. Okay. This one higher maneuverability. This one higher efficiency. Macam tu lah. Okay lah. Ni lift due to spinning. So hello. Okay. So this is what we call the Magnus effect, producing lift by rotation of solid body. So why would it generate lift by spinning? Why isn't the why does it generate lift? Okay, because when you rotate a body, it will directly affect the the velocity of the flow over the body. Okay, like this. Let me explain. Sabar. Okay. So when the body velocity is against the velocity of the fluid, it will have a very high friction. Betul. If the body is same direction of the flow, it will have very low friction. Okay, so what does that mean? What does that mean? It means that when low friction, it allows to have a very high velocity. If it's higher friction, it allows very low velocity. So where there is high velocity, there is low pressure. When there is low velocity, there is high pressure. So there is a lot of pressure pushing up this body, but only a bit pushing down. Okay, so what we get is lift, because there is much more higher pressure pushing down here than up here. Okay, so that is how basically you generate lift by spinning. So you can see here, this is just me explaining it. This is already in your textbook, don't need to worry. So this is double slot, single slot, something like that lah. So this is actually which topic okay, so this is CL, angle of attack. Okay, this is when we store. Okay, iPad ni menguji kesabaran lah. So slot here, slot 1, 2, sini 1 je, sini tak ada slot. Slot prevent the separation of the boundary layer from the upper surface and increases the lift coefficient. Why does it increase lift? Because it increases the surface area. Why does it prevent separation? Because there is little holes that fluid can enter. And okay, what can I say? So this is what happens when a fluid separates from a body. If somehow we can decrease the length here, how we would do that? We would start another surface. Let me show you. Okay, imagine you have one surface. So the flow separation is like that. But if you have two surfaces, the flow separation will restart again. Macam tu. So wait, it's not supposed to be like that. It's supposed to look like this. Sikit je flow separation dia. Macam tu lah, something like that. So that is what it means to prevent separation from the boundary layer. Okay. So that is a lot of applications that you guys need to look into, because I don't know what esok akan masuk. Usually airplane airplane flaps is usually slotted. Masuk past here is the F1 rear wing, which is called the drag reduction system. You guys should also see the F1 front wing. Front wing tu. This is okay. Now let me show you. F1 front wing. So yeah, where do we start, bro? Okay, so back in the old days, the wings were only like 1 and 2. Oh my god, what happened? What the heck? Okay, this is only like 1 and 2, but and then they change. They have like 1, 2, 3, 4 slotted flaps. That's how impressive the downforce that they generate. Okay, so you can see lah. You can see I tak nak lah cakap pasal F1 ni. Boleh cakap satu hari tu. Anyway, apa lagi application? Tak ada kot. Korang tengok dulu lah tu. Airplane flaps, rear wing, front wing. Okay, so that is all from external flow. Okay, so wait, let's wait for this to load. Okay, so if not, we go to pump characteristics. How to answer. Wait, let me get how to wait, where's my phone? Someone call me. Okay, how to do pump characteristics. Okay, so before we start, do you guys want to take a break? You guys can take a break. Wait, kita santai jap. Aku penat. Okay, take break. Take five. Kita jumpa 11:25. Okay, take break. Take 5. Kalau ada Twitch streamer kan, dia ada macam iklan 5 minutes. Tapi aku tak ada, sebab aku punya OBS ni macam haram. So tak apa. Okay, so sambil-sambil tu boleh lah minum air ke. Minum air ke. Payah rambut rasa. Susah payah rambut. Esok pergi exam handsome dah. Ambil gambar. So korang ada nak luahkan apa-apa ke, tanya soalan ke? If you have any questions, kindly put your questions in the chat box. Nasir, cuba explain graph untuk golf ball. Oh, okay, boleh? Sure. Okay, why not? Why not kita tengok YouTube? Sekejap. Aerodynamics. Okay, aerodynamic drag. Wait aku selalu tengok dekat sini tu. Sekejap where dia explain? Sekejap, dia ada explain somewhere here. Okay, this is pressure drag. Golf ball. Okay. Lepas tu friction factor untuk pump performance kau rasa boleh constantkan ke? If the friction factor is small, you can constantkan lah. Okay, wait, let me explain this. So okay, welcome back. This is just a short, kita sentuh sekejap je. So this is assume the golf ball. So at higher velocities, okay, velocity is high, the Reynolds number is also high. So you can assume this to be like a graph lah, like a graph. So when the Reynolds number is like, what's this? This is something around 1, 2, 3, 4, 10, and 4 is 8, 7 Reynolds number equals to 7 times 4 here. The CD decreases. Why does it decreases? Because because the flow separation from the surface of the golf is designed to because the design of the share screen. Oh shit, aku tak share screen. Sekejap. Maaf. Okay. So assume the velocity to be very high. I mean, when the velocity is high, the Reynolds number is also high. Increase lah. When the velocity increases, the Reynolds number increases. So over here, we can observe that the coefficient of drag decreases. Why does it decrease? Because the design of the the design of the surface of the golf ball is to maximize flow, reduce flow separation. Macam tu lah. Only at certain range of Reynolds number. Something like that lah. Sebab apa? Sebab okay, korang kena tengok video yang video ni. Okay. Korang boleh dengar? Boleh dengar. Kalau boleh dengar, cakap. Tak dengar ke? Okay, tak apa. Tak dengar. Okay, tak apa. Without separating. Okay. Because we can also note that rough surfaces allow the flow to separate later when at certain ranges of Reynolds number. Tulis tu. Rough surfaces allows flow separation to occur later at certain RE. Scientifically I don't know why, but just tulis lah something like that. Okay, now kita masuk pump characteristics. Okay, I hope everyone is ready. So now it's 11:30. My parent is on the way. Sekejap. Sekejap sebentar. Paste, go. Share. WhatsApp. Miki, mana Miki? JKM. Okay. So if you guys want further explanation of the golf ball, you can watch the video. I learned from that video lah. Okay, so now this is a question from past year 2000. Okay, thank you. This is a question from 2000. Tak ingat. 2021. 2021. So let's read it together. Project engineer, you asked to evaluate the operating condition of piping network connected to a pump. Taco model 4013 rotating at 1160 rpm. Basically, the pump draws water at 20 degrees Celsius from reservoir 1, reservoir 2 to 90 millimeter diameter. Water level is 2 meter, water 7 meter. Okay. You can find this document in the... Wait, I have not shared this lah. I share to you guys dulu lah. Sekejap, export this page. Export PDF. Sekejap send. Sekejap. Send file, WhatsApp. Okay. Huh? Okay. Okay, dah hantar. Dapat tak? Tak dapat. Sekejap. Okay. So from the question here, you guys can read it. So what we want to consider is, okay, first this is the RPM 1160. This is the temperature of the water. From the temperature of water, you can find the P saturation, density, dynamic viscosity, diameter, and the flow rate. Okay, so open your textbooks. Open to... This is table saturated water. Okay, this is table A3. Go to table A3, page 950. Okay, so go there, and then you will find this other details lah, which is the P saturation, the density of water, the viscosity. Okay, so for our first question, it asks us to select a suitable piping material for the operation of the system and clearly state your reason for such selection. Evaluate and clearly describe the minor head losses considered in your system. So first thing first is to decide the pipe material. So I decided to go with brass. Why do you go with brass? Because we go here. This is external flow. Go to internal flow. Where is internal flow? Wait, this is internal flow. Internal flow. Okay. So this is important kan, tadi I ada cakap yang all this material ada dia punya roughness dia. So brass has a roughness of 0.0015. That is actually very smooth and approaching to zero. Approaching zero. Okay, so I choose brass tubing. Where is this? Okay. So you brass tubing. So aku ada tengok lah internet how to choose the right plumbing pipe. So there is a lot of plumbing pipe and all of this is in the table, but you don't know which to choose. You can just choose PVC, you can just use steel. Isaac choose galvanized. I choose brass because it says here it's used for water tanks and wells. So cast iron, water distribution system, copper, hot and cold water. Galvanized is used for grey water. Grey water is used water or recyclable water, something like that. PEX is like a composite lah, I think. I don't know, not sure. PVC is used for hot and cold potable water. Potable is like drinkable, tak silap lah. Drinkable, I don't know, I tak ingat. Dia macam dia tak ada kuman lah, something like that kot. Stainless steel ada juga. So what I choose is brass. Okay, so you need to like list down the reasons why you choose brass. Usually used applied for water tanks. Resistant to corrosion. More durable. Is relatively smooth. Dia punya roughness is 0.0015 mm. Okay, so it also asks us to evaluate and calculate the, not calculate lah, evaluate tu calculate lah kan. Clearly describe the minor head. So this is the minor head loss. We have two type of head loss, minor and major. We have minor and major head loss. So we want to find the minor head loss. Minor head loss, where's my phone? The minor head loss is due to the components. So I already highlighted here how much components we have. We have 2 flange elbow, ball valve, 3 flange elbow, check valve. Okay, so altogether we have 5 flange elbows, ball valve, swing, check valve. So you go to page 383. Okay, cuba you guys buka page 383 ni. Cuba korang buat. Sekejap, sekejap. Yang tadi tu kan, yang tadi tu. So dia banyak-banyak dia punya coefficient dia, flange ataupun threaded. So you will find the coefficients here. So okay, all you need to do now is to find the total minor head loss. Total minor head loss is like this lah tadi, cuma tambah je KL dia. So we need to find the V. So how do we find V? We assume that the V suction is equals to the V discharge, because the diameter does not change, because the diameter is constant. Kan I mention tadi, if the diameter isn't constant, the velocity would be different. If the velocity would be different, the H will be different. So you need to calculate separately. But lucky for us, it has a constant diameter of 90 millimeters. It has constant diameter of 90 millimeters. Okay, so that is why I assume V suction is equal to V discharge. Okay, so ni okay, all those calculating lah, and in the end you get 4.4634 millimeters per second, and then you put into the equation, you will get 3.6. Okay, so that is the minor loss. Okay, so now comes the big one. Evaluate the operating point. The keyword here is operating point. Operating point of this piping system. Sketch plot of head required and available as function of volume flow rate. Okay, so you guys don't know what to do first. So what you guys do, okay, this is how you actually like do step by step. They don't like really teach you what to do, so I'm gonna teach you what to do. So first you need to find the horsepower required, and then you need to find the horsepower in function of flow rate, and then you need to make a graph. So that is exactly everything. And also self-priming, because the water will be always flow through the, there will no be air bubbles equation. Oh my god, Okay, so tulis, then P0 because both is reservoir exists at 1 atm. V0 because there is no difference in velocity, because we assume that the flow rate is constant and also the area is constant. Flow rate over area, velocity constant. L over D times V2 squared, V squared over 2G. We need to find F, friction factor, using Harlan equation, because it is turbulent. Wait. Why do we use Harlan? Because it's turbulent and it's considered to be rough. How do I know is it turbulent? Carilah. We don't know the RE. It is not laminar lah. It's not laminar because it's much bigger than 2300. So it is considered to be turbulent. So you can see here actually that the roughness is like dah sikit sangat ni. Kalau korang letak calculator, dia jadi macam 1.6667 darab 10 kuasa negatif 5. That is actually very small. So that is why I choose brass. That is why I choose brass, because it has a very small roughness considered to the other material. Find the friction factor. I use this friction factor using the calculator. Easy je actually. So you get 2.6 times 10 to the power of negative 3. If Isaac uses galvanized, I don't know, something galvanized iron. Kau guna apa Aku lupa. Okay, never mind. You will get FD equals to 0.024 something. So this is much higher friction than this. So this is lower friction. So my version has lower friction. Okay, so we know this value. We can input this value into the equation. We will find that the major head loss is actually 0.73. Ni major head loss ni. Major loss is 0.73. Minor loss is 3.6. Okay, aku pun sebenarnya tadi macam fikir kenapa minor loss dia banyak, kenapa major loss dia sikit. Satu, dia punya length ni panjang. This is 25 meters. Okay. Dua, there is a lot of components for the minor loss. There are like 7 components altogether. So in the end, I will get the total head loss is 4.338. Sini. So I dah jumpa dah HL. So we put into this equation, you will find that the horsepower required is 9.338 meter at 450 gallon per meter. Remember this. Don't leave this out. Remember. Okay. So you found the horsepower required. Well done. Now you need to find the horsepower in function of flow rate. The horsepower in function of flow rate. How do we do that? Okay. So we like retrace. We retrace from this equation. HP equals to delta Z plus HL. Okay. HP equals to delta Z plus HL. We plug in delta Z 5. We plug in the HL, but this time the velocity we leave it out. Because the velocity is directly proportional to the flow rate. Flow rate. This is flow rate. Wait. Alamak. Okay, sekejap sambung tadi mana? This is flow rate. So it wants the function of flow rate. So this is what we got. You put inside here. You calculate this, and then you will get this. This is the equation. This is the function. This is the function. Fx. But this time it is h over macam tu. Something like that lah. Faham tak? Okay, so this is the equation that we need. So as you can see, it is actually a quadratic equation. So what happens if the flow rate equals to 0? So this will equal to 0. And then if the flow rate equal to 0, this will equal to 0. H will equals to 5. Why? Because over here dah ada 5 dah sini. Sekejap. Kalau ni 0, tinggal ni je lah. So horsepower required is 5. Okay. So this is the important stuff. This is it. So this is, why is it so small? Fuyo. So this is horsepower. This is the pump curve. Equals to 5 plus you have orang kata apa? Constant. You have a coefficient here, and then you have flow rate squared. This is the system head curve. Okay, the pump curve is the blue line. The system curve is the white line. What do I mean by blue line and white line? It is here. Uish, mana kau dapat graf ni, Nasir? Dari sini. Okay. Okay. So after finding the function of the flow rate, you need to make a graph. Kenalah buat graph ni. Graph ni korang letak satu-satu flow rate. Tak kisah 400, 200, 300. As long as you have 0 and 450. Tu je. Okay. When it is 0, head is 5. When it is 450, head is 9.3. So you graph macam tu. Okay, so that is the first step. Wait, I think better I padam ni dulu. 1, 2, 3, 4, 5, 6. Okay, clear tak? Okay, so you put here. This is 450 gallon per meter. This is 0. This is 5. This is 9.3. So you graph like that. So you need to graph, like legit draw a graph and not just trace on this, because this is actually very confusing. So you need to draw separately. Okay, and then when you draw, you will like see whether, okay, so this is your 9 is like supposed to be here lah, somewhere here. Wait, somewhere here. Okay, so this is like 450 somewhere here, and then see where it intersects. It intersects over here. Okay, so usually it will intersect like if you follow Isaac's solution, it will intersect right about 15. It will intersect right about here lah, because he uses a different material. It will have a higher friction, thus having a higher horsepower required. but I use a lower friction material, so I require less horsepower. So there's nothing wrong, it's just that we need to improvise lah, because it tak kena sangat. Kalau you tengok sini tak kena sangat. You're supposed to like hit that on here, but it didn't, so never mind. Kita teruskan je. So what we can do is plot the graph here. Okay, so this is the graph here, and then we can see that this graph, this is the blue line that I'm talking about. This is the pump curve, blue line, pump curve. Okay, let me just, tak nampak siap. This is the pump curve. This is the pump curve. This is the system curve. This is the intersection. Why do we need the intersection? Kenapa? Sebab it is equal. There is where it intersects. So you need to find the operating point. This intersection is called operating point. Tapi sebabkan kita kena, kita just cakap this is just an approximation. So the horsepower is actually higher than what we actually need lah. So it's okay, don't worry. If masuk exam esok, korang pandai-pandailah kena-kenakan dia. Tapi if tak kena, korang just ambil yang paling dekat, yang kat atas. Jangan ambil yang bawah, sebab yang bawah will have lower flow rate. Ambil yang atas. Okay, so that is basically how you answer it. Okay, so and then dia akan tanya, justify the appropriate impeller size. Okay, so kan sini ada banyak kan blue curve ni. Ada pump curve 1, ada pump curve 2, ada pump curve 3. So the difference is the diameter of impeller. The bigger the impeller, the more flow rate. No more flow rate ke? The more head, more horsepower, and generally is much more efficient lah. Generally bigger impeller is much more efficient if you refer here. If you use small impeller, the efficiency ranges from like 50% to 65%. If you take the big impeller, it hits 80%. So the more you know. Okay, so for me, I will take the closest to my operating point, which is 9.75. What is your opinion on the operation efficiency of the pump? Please clearly describe your reasons and suggestion. So over here, okay, so what is the green line and what is the red line? The green line is the efficiency. Okay, so because kat situ macam semak, kita lukis kat sini. Because this two plane curve is not important, we ignore this. Okay, so what is important here is just these two. Wait. This one. Okay, so this is the operating point. Sekejap, kau apa ni? Okay. Mana phone aku? Okay. Ready? Efficiency. So the efficiency is like that. Macam tu ke? Macam mana? Something like that lah. Something like this lah. Something like this. Not accurate lah, but you get the question lah. So usually if you find yourself in between the efficiencies, you can just take the average. You can estimate. For example, you have here 70 and 72. So if your operating point is in between, you can assume that the operating point is at 71%. Okay, so that's what I did. Okay, so over here clearly don't have any intersections, so you approximate it for this to be 71%. So describe your reasons and suggestion, Papanella. And then here you need to evaluate the net positive suction head, NPSH. NPSH ni apa? NPSH ni graf yang ke atas ni. Graf yang ke atas ni is the required head for you for the macam ni lah. How high the pump can go before anything goes bad. Okay. So this is the pump. So the pump is not supposed to be above the reservoir. Not supposed to be above reservoir because satu, it may not prime self prime sekejap, cause cavitation. That's the word, cause cavitation, because when P equals to P evaporation of water, it may cause bubbles. Okay, so this is like a safety measure by the company. They give you a curve and then you need to plot where is your pump, how far can you bring your pump, macam tu lah. So over here you plot here and then you tarik ke kanan, you put over here. So over here is like 15 kilopascals. Okay, bear with me. So this is the equation. PATM. Oh my god, I'm offline. Okay, sekejap, I dah on balik. Okay, so then this is the head loss from the total head loss tadi, and then you will get this. If HL equal to 0, you will get this. Okay, what's that mean? It means that is the maximum height the pump can be placed above reservoir level. Okay, so if above delta Z, water will vaporize. Okay, itu saja. That's all. So do you guys have any question regarding anything? You guys can hello. Okay. Short ke tadi? Soalan ni macam bully kita je. Soalan ni dia memang panjang sikit tu je. Okay, bukan macam malas ni. Okay, so wait before that okay, bye guys. Good luck for tomorrow. All the best. Thank you for watching. Bye bye.